Now let us talk something about the self-heating and the spontaneous combustion. So, self-heating means if I have vegetable oils, so you can say that sunflower oil, rapeseed oil, etc., the vegetable oils which are high boiling point, that means its flash point, fire point also can be higher. If these oils are saturated in a porous substrate like saturated fabric materials which are porous material substrates, and this vegetable oil is saturated over this, then if it just keep it in room temperature also for a long time, then you can see that self-heating can happen. That means there is some heat which is generated due to the vegetable oils decomposition. We don't need any external heat or anything, just kept it open to the atmospheric air, it may cause self-heating. This occurs due to the changes in the structure of the fuel. Okay, so once the temperature increases, some vapors are produced and some flame can be produced, or the strong chains, so carbon rich chains can be heated to a temperature which can attract oxygen from the ambient and form smoldering. So these are all very not high heat release combustion. The spontaneous, the self-heating or spontaneous combustion are not very high heat release. They are like smoldering, where the temperatures are restricted, say below 500 degrees, 600 degrees, etc. And but there will be decomposition of the material, formation of smoke, and oxidation, slow oxidation will occur. So the slow oxidation process is not triggered by anything. It is just due to the changes in the structure of the fuel, which is actually accumulated over a porous substrate like fabric material, and this happens for vegetable oils type of vegetable oil type of liquids, where this is composed of several fatty acids and they are very viscous. So this is called spontaneous combustion. So the self-heating acid, that is when you have this, if it is stored in liquid form, nothing will happen. When this is actually saturated over a fabric material, porous substrate, then you have this problem. This acid of self-heating is listed in increasing order. That is, coconut oil has the least, and the tung oil has the highest acid as self-heating acid. This is because of the increasing value of the iodine numbers. For example, coconut oil has the least iodine number, and increasingly olive oil, cottonseed oil, soybean oil, sunflower oil, etc. will have. Finally, tung oil has the highest iodine numbers. So the iodine number is nothing but the mass of iodine in grams, which is consumed by 100 grams of oil or saturated in 100 grams of oil. Okay, now this self-heating is one of the phenomena where for special applications we can see this, and we have to be very careful in handling the oils like tung oil, linseed oil, etc., which has higher hazard. Reactivity of a substance to oxygen depends on double bonds. That's what this vegetable oils, etc., will have saturated as well as unsaturated components. The unsaturated components basically has double bonds, etc. So their reactivity will be very high. So this is about this self-heating or spontaneous combustion. So piloted combustion, we need external source and minimum volume of premixed reactants, flammable reactants should be available, minimum ignition energy should be given, location should be properly located where the flammable mixture exists. Then second is auto ignition, the mixture is formed but it is in contact with the high temperature gas or any metal or any surface where it can auto ignite. The mixture reach the auto ignition temperature and there is no need for any external ignition. The third type of ignition process is the self-heating or spontaneous combustion. Then we move on to seeing ignition delay. The ignition delay is nothing but ignition time. When you start your ignition process, how much time it takes to ignite or see a visible flame or a flash, etc. That is the ignition delay, which is the sum of evaporation time, mixing time and induction time. Evaporation time, you know, the time it takes for the fuel to evaporate. That is the rate of evaporation. We have seen m dot double dash. That is the mass which is evaporated per second per meter square. That is the evaporation rate. So, based upon this, I will get a evaporation time. Then mixing time. Once the vapors are formed due to evaporation, the vapor and the ambient air mixes. It needs certain time. Okay. So, if it is by pure diffusion, it will take a longer time. If there is some convective environment or turbulent environment, the mixing will be much faster. The third time is called induction time, which is the time required to commence the chemical reaction. Once the mixture is formed, it has to be ignited or it should reach the auto ignition temperature, etc. So, basically to start the chemical reaction time may be very less, but to start the chemical reaction there may be small delay. That is called induction time. But you can see that when we have certain natural convection environment or forced convection environment, the mixing process is enhanced so that the mixing time reduces significantly. Similarly, when you use pilot ignition or if the mixture reaches auto ignition condition, the induction time actually reduces very close to zero value. That means the evaporation time is the one which controls the ignition time or ignition delay. So, the time for the fuel to evaporate, liquid fuel to evaporate will dictate the entire process, the rate limiting step. Now, ignition is caused. Okay. So, let us consider a long pan with fuel and ignition is now caused. So, I ignite it at a particular location and a flame forms over this location. It is unlike a small beaker, it is a long trough where the liquid fuel is kept. So, locally I ignite somewhere, a flame is formed over the surface and this flame now will heat the subsequent neighboring portion and the vapors are generated. So, it will move on. The flame actually spreads over the liquid surface. So, the next process is the flame spread over liquid fuel surface. After evaporation, ignition, flame is formed and the flame now spreads over the liquid fuel surface. So, this basically is transient in nature. The flame propagation is transient in nature. It is dependent on several conditions and it may be rapid, it may be gradual, it may be steady, it may be unsteady, etc. So, the flame spread process is the next process where after ignition the flame will try to consume or heat up the adjacent fuel layers and cause vapors to come out of that and form transmit itself over the fuel surface. And this flame propagation, which in general is transient, depends upon first fuel property, then initial fuel temperature, then the ambient conditions. Ambient conditions means ambient temperature, ambient pressure and so on. Then the strength and direction of the convective flow. Okay. So, let us see one by one. For example, the primary fuel properties which will dictate the flame propagation are the same that will dictate the ignition, like flash point and fire point, because when the flame has to spread over this surface, basically what happens is the flame should ignite the subsequent layer or subsequent neighboring points and spread over that. So, it is like subsequent ignition as the flame propagates. So, the main fuel properties which can affect the ignition like flash and fire point and etc. will also affect the flame propagation or flame spread. Now, initial fuel temperature. When the fuel temperature is less than the flash point, then it has to be first heated up to flash point, then only vapors will be produced, or it has to be heated to the fire point where sufficient vapors are produced for the flame to propagate and so on. So, the initial fuel temperature, if it is very low, then the flame propagation or flame spread rate will be low. Then the ambient conditions, if ambient temperature is low, then the heat release from the flame can be lower than the heat which is lost. So, the flame will not spread. So, the lower ambient temperature also will affect. Then coming to the strength and direction of the convective flow. Here we classify the flame spread rate as concurrent flame spread. We have already seen this concurrent and opposed. If the take this example of this long trough where ignition is occurred in the left end and the air is flowing from left to right, then that is the concurrent flame spread or flame propagation where the flame spreads in the direction of the airflow. So, this will be rapid because when the flame forms and the air flows in the same direction, then the flame actually bends over the surface of the liquid and the heat transfer is enhanced. Longer length after the ignition location is heated, so that more vapors are produced and the flame propagates in a rapid manner. On the other hand, when you ignite in the left edge and the flow is from right to left, that is classified as opposed flow where the flame is trying to spread in the direction opposite to the airflow. So, this is the in this case what happens, the airflow opposes the flame spread, so that the flame actually heats up a small or very small portion ahead of it and slowly or gradually propagates. So, the flame spread rate in a concurrent airflow direction will be much faster than the opposed. Okay. So, the concurrent, the oxygen flow is the same direction as that of the propagating flame. So, it will be very rapid, and in the other case it will be very slow because of the opposing airflow. Now, in this horizontal case where the flame spreads in the horizontal direction, forced convection plays a role. But if you take a wick which is saturated with the liquid fuel, so this is the wick which is saturated with liquid fuel, and try to ignite it here, a flame forms like this, and gravity is in this direction. So, the natural convective flow is created in the direction opposite to the gravity, that will be in the direction of the flame spread itself. So, that is concurrent flame spread for the natural convective flow. If the flame spreads from top to the bottom, then the gravity flow, aided flow will be in the opposite direction, that is opposed flow. So, in both natural convection and forced convection, we can have both concurrent flame spread as well as the opposed flame spread. So, what are the factors that will affect the flame spread? Concurrent flame spread is very rapid, and due to the rapidness, that is the flame accelerates etc., it is also very hazardous. Here, as I told you, why it is rapid, because it heats up a longer portion of the surface ahead of the flame, so that more vapors are produced and the flame actually propagates at a faster rate. In the opposed flame spread case, the heat transfer from the flame to the fuel surface and the mass transfer processes are affected by the oxygen flow. So, first of all, a small portion is heated, so limited amount of vapor only will come out. Then there is a convection in the opposite direction. That means the heat release, that means some heat loss due to this opposed convection also, and the flame will not bend towards the spreading direction, it will actually bend up, so that the flame standoff from the liquid surface will be low. So, the heat transfer will be low, corresponding mass transfer also will be low. So, The opposed flame spread will have a very low speed propagation, but the flame spread will be very well defined. Here the flame in the opposed direction, the flame is very well behaved. That is, if this is the direction of airflow, a flame forms, the flame is very well behaved and this actually moves slowly and consumes. But in the case of concurrent flow, the flame actually forms over the entire surface, heats up rapidly, and there are several physical aspects which happens, and the flame actually will be not well defined basically. So, because it grows at a very fast rate. So, the rate of flame propagation in both concurrent as well as opposed flow modes are influenced. In both the cases, this is influenced by whether the fuel is above or below its flash point temperature. That is very important. So, as I told you, because these are subsequent ignitions, when the fuel is at temperature which is more than the flash point, then enough vapors are available. If it is less than, then the flame has to heat up the fuel to the flash point. So, that is the first step it has to do. First process is the sensible heating of the liquid to the flash point temperature at least. So, that is the important point. So, when the liquid fuel is above its flash point, when it is above the flash point, sufficient vapors are generated continuously, because that is the condition where enough vapors can form a flash. So, now this flame will act as a ignition agent and try to ignite the vapor air mixture formed subsequently, and it will spread. So, the combustion mixture of fuel and the oxidizer or air is present everywhere over the fuel surface because of the fact that the temperature of the fuel is more than the flash point. So, what happens? The flame spreads at a faster rate, as though the flame is spreading consuming a premixed gaseous reactant. So, the heat up is not required, okay, it just spreads faster. Then it is going to anchor over the entire fuel surface and consume the fuel, liquid fuel itself. That is the third stage. So, now in this case what happens? When sufficient premixed reactants are there, then the chemical kinetics affects the rate of flame propagation. Okay. So, in these cases the flame spread rate can be as high as 1 meter per second. 1 meter per second. So, that is very high flame propagation rate. So, this is a very dangerous situation. So, class 1 fuels, low flash point fuels can display a very fast flame spread over its surface when ignited. Then the other extreme case, the temperature is now below its flash point. The temperature of the liquid is below its flash point. So, the mass transfer process will be the rate controlling. That is, slowly the surface has to be heated, vapor should come out, form a mixture, and the ignition will occur by the flame. Okay, so now it is very gradual, and so at the rate at which the vapors are evolved, as the liquid is heated up, that will be the rate controlling. Kinetics doesn't have anything to play here. So, that is the just extreme condition when the temperature is below its flash point. So, sub flash point liquid, when the temperature of the liquid is below the flash point, sufficient amount of vapor and air within the flammability range will not be available. So, the flame which is propagating has to preheat the downstream liquid surface to its fire point, so that enough vapors are produced. Flash point to form a flash, but fire point to sustain a flame, such that a sustained flame is formed subsequently and the flame propagates. So, in this case what happens? When there is a liquid and there is a flame which is formed over the one of the corner, then there is a heat transfer here. So, that means this part of the liquid surface will be higher at a higher temperature, and subsequently the temperature reduces as you go downstream. So, this point where the temperature is higher, the surface tension will be low and the surface tension will increase as the temperature decreases. So, now due to the surface tension gradient, there will be a movement of the layer, there will be a movement of the surface from the high temperature to the low temperature point. So, that will cause some internal circulation. So, that is basically can be seen when there is a sub flashpoint liquid. So, the sub flashpoint liquid basically causes some internal circulations also. In this case, the movement of this surface can cause recirculation, that will also enhance the evaporation rate. That is advantage in this. But if you take a case where the fuel is set more than the flashpoint temperature, then the liquid will not contribute to anything, because already vapors are available in the vapor phase and the flame will just go and consume those vapor air mixture. That is it. So, the liquid heating becomes a secondary process after the flame has formed over the surface. So, further it will be heated to more than the fire point temperature and it will reach the equilibrium temperature whenever the flame has completely spread over the liquid surface. But in the case of sub flash point, there are several physics. One is the sensible heat which has to be given, the rate at which mass comes out of the surface and the motion which is triggered due to the temperature gradient which has caused the surface tension gradient. So, the liquid phase transport process will also become important when the liquid temperature is sub flash point temperature. So, the spread rates will be appreciably low because you have to heat it. That heat transfer and the mass transfer process, which are generally slow, will dictate the flame spread rate. Now, the flame spread is controlled by several aspects. So, in that way we can classify them also. The flame spread is classified as liquid controlled regime, gas controlled regime or asymptotic flame spread. Okay. When the liquid controlled regime comes, where the temperature is less than some flash point, just we have discussed this, where the liquid heat up, the liquid motion, etc. comes into play. So, the transport process in the liquid phase is there and that is significant and that controls the flame spread, that is the sub flash point. Gas phase control, when enough vapors are available in the gas phase, based upon the convection in the gas phase or temperature of the ambient, etc., the flame spread rate will be there. That is called gas phase control, where the liquid has already gone past the flash point or fire point. Then third one is asymptotic flame spread. Okay, in this regime, the flame spread rate will be constant and will not be sensitive to the liquid temperature at all. That is the third classification. So, we have liquid control, that means liquid phase transport process will control the flame spread rate, especially when the liquid temperature is at sub flash point. Gas phase control when liquid is already more than the flash point or fire point. And in an asymptotic regime, the flame spread will be constant, insensitive to the liquid temperature. So, these are the factors affecting the flame spread rate. So, now let us see flame spread over methanol pool, where the methanol, say flash point of methanol is about 15 degrees and its boiling point is also quite low. And this is the experimental results of Akita, where here clearly shown that when the initial methanol temperature is varied from -20 to 30 degrees, the flame spread velocity is plotted. So, at very low temperatures -20 to -10 degrees, what happens? You can see that the flame spread rate is not varying much, it remains almost uniform. So, this regime is called pseudo uniform region. Now, temperature increase from -10 to about say 5 degrees or something like that, or say 2 or 3 degrees, then you can see there is a increase in the flame spread rate about 1 meter per second to about 10 meter per second increase is there. And here the flame propagates to the downstream, then again quenches there, come to the upstream, then so that means there is a pulsation of the flame spread. It is not just traveling from left to right continuously, it goes to a point downstream, then comes to the upstream, then so it oscillates while spreading. That regime is called pulsating regime when the temperature is in this range. Then the third one is called the uniform regime again. So the first one was pseudo uniform, the second one is the pulsating, the third one is uniform regime, where you have the flame spread rates plotted here, and the temperatures are say 2 degrees to 11 or 12 degrees. So in this regime the flame spread becomes uniform, small variation is there, linear variation is there. Then when you go from say 11 or 12 degrees to 20 degrees, you see that there is a good increase in the, because of the fact that now you approach the flash point temperature, go beyond that, and enough vapors are already formed. Now you have the flame spread which is not at all controlled by the liquid phase. Now gas phase is going to control it. So it is like a premixed type flame spread where the flame spread rate increases. Finally, this is asymptotic region where once the liquid or the fuel temperature is more than say 20 degrees, then the flame spread rate remains constant at a higher value. So this is the basic trend for methanol, where you can see that the initial fuel temperature affects the flame spread rate very thoroughly. So to summarize, I can say that the flame spread in sub flash point aspects, okay, the liquid fuel does not remain stationary because of the Marangani convection. The Marangani convection is caused due to surface tension gradients. A recirculatory convection current is observed ahead of the flame because the flame is heating the surface, so that is at a higher temperature. Downstream that temperature reduces, so there is a temperature decrease. So the concentration of surface tension gradient forms, or then due to which from low to high surface tension the fuel surface flow is triggered. So now this recirculatory convection current is observed, and that actually aids the flame propagation. The recirculation subsurface flow, liquid move from a point away from the flame to the surface. So from the surface where the flame is there, the liquid surface moves and returns back at a certain depth. So this recirculatory zone will enhance the mixing or the heat transfer to the liquid surface, liquid phase. So the heat transfer to liquid phase is enhanced by this recirculation zone. Then, as I told you, the temperature gradient induces the surface tension gradient, and that causes the Marangani convection. So this is another important aspect of the sub flash point. So the liquid phase heat transfer, mass transfer, etc. controls the flame spread. So I will stop here.